So, hello everyone. So we are meeting on monthly meetup in EPFL about machine learning. And today we're going to have Joël Grognuz, who is going to be presenting his topic on making connection between simulated data in computer and real engineering when you really want to build something from out of this data which he is generating. We are actually meeting once per every 6 to 8 weeks, depending how we have available time for organizing these meetings. And each time we are having apéro after the meeting, which is going to be held downstairs on the main hall or here just next doors, depending also whether other people are going to be there. So I'm going to tell you a little bit about Joël. I prepared a few words about him. So I met Joël like 7 years ago, and he made a really good impression on me from the very first moment. And as a very professional, and come here. And this is also first time when we are recording it, and all meetups from now on going to be available online on YouTube and on our site. So if you cannot come, you can also check it in future meetings and log in. I hope it's not going to completely destroy our attendance. So about Joël, he did his master here at EPFL and finished it in 2003 with his project, as I understand, in Plasma Center. It was already a Plasma Center?
Yes.
Yeah, so in Plasma Center working on tokamak. After this, and also before on stage, he was working in CERN, where he was working on cooling systems. First on cold cooling systems, water and liquid nitrogen, and then on warm with a liquid CO2, yeah? Or
gas CO2.
Okay, gas CO2. And from 2008, after 5 years of, and actually what I found on his internet site, the cooling system was used with a detection of Higgs boson in CERN in Atlas experiment. So really cool stuff. And
cool is the word.
yes. So in 2008 he started to work in CADFEM, actually the company who is paying for our booze after the meeting. And we are thanking very much to the company and other people from this company who are also interested in our topics. And the company, maybe you're going to present what they are doing. So, please.
Thank you, Pawel. I'm going to try and give you some insights in what we are doing and the relationship there could be between this modeling we are doing by CADFEM and the machine learning. So CADFEM is actually a competence center for finite elements modeling and finite volumes modeling in Switzerland, and we are representing a software called ANSYS that we are using for consulting, for teaching to our customers, and to sell the licenses as well to the customers. So basically, our value is that simulation is more than software. It's just not software only, is more. And now we are going to go beyond simulation. We are going to be the use of and the usage of simulation in smart products, and that we can see nowadays already, and that we are going to see more and more in the future. So it started, I just want to go slightly back about humanity and what people were doing. So in the past, we were already modeling. We were creating representations of our world just to transfer ideas, to explain something, to plan something. Who knows? But there was already someone here speaking to others, I'm trying to act as a dignitant of a heritage left by this guy, and I'm going to do the same today, basically. So the only difference is that our models are slightly more evolved. So the guy was stuck there. Now we evolved a bit further. We are using these machines that are helping us. And this is pretty much what I'm doing every day. Today I was there in my computer preparing this. And we're going to use this a bit further. So the story is not yet ended there. So what we're using, as I mentioned, finite elements modeling and finite volumes. What is that? Just on one slide, because I know you've been at school, you've seen this type of stuff, but this is what I'm going to show afterwards in nice movies and pictures. But behind these pictures, behind these animations, there is this type of discretization, basically taking reality, CAD models, 3D models, 2D, 1D models, chopping them in small blocks, attaching degrees of freedom to these nodes that allow us to solve the physics equations. We can model it also in 0 dimension with blocks in the Laplace space, for instance, in order to solve dynamics of systems and have models that run much faster, which is also quite useful for machine learning or for smart products. So that's the space discretization. Then there is the time discretization. So we can analyze something as a static object in the frequency fields or in a transient time domain. So that's a way also to deal with different type of physics, different fields of physics. We call this multiphysics, having different degrees of freedom, solving this in different time frames. You see here an example. If you had an electronic device with a current, that would be the red line, a harmonic response. The blue one would be the power generated by this. You can assume that it is constant over time, so it's stationary, static. And then the green line would be, for instance, the temperature in the device. That's a transient simulation, and you see there are effects, inertia effects, heat capacity effects, and so on. So it's a way to deal with different physics, but with different ways of discretizing this. And this is the role of the human, of the engineer, to choose wisely in these domains, in these physics. And then you can couple this, take one domain, you see here transient, another one harmonic, another one static, and you can mix them together, forming a puzzle that would be your model representing the physical reality, basically. So that's very briefly explained. This is the topics dealt with in a course of a semester or a year at EPFL. So yeah, it was a bit fast. Now let's see how it looks like nowadays using these simulation tools. So we are going to take a look at an example that is quite trendy. So a drone. What can we do with this type of models? So we can really represent all this. So okay, there is a bit of CGI to put all the physics results together, but all the colors are coming from the physics simulation tool. So we can start from every component, the motors, the wires, the electricity that is provided by the heart of the drone to the motors, the signals. So now we're reaching the brain of this drone. And on the brain here we have several connections, so the PCB basically, and we can study all this in details. So the idea is to have a virtual prototype of this whole system. You see here all the impulsion, all the signals that are traveling from the board in the middle, the package, to the extremities of the PCB and then to the rest of the system. The interesting stuff here is that, okay, you have to design a layout that is going to work without too much interference. We can also model the inside of this brain, of this package, and the coupling between the package and the PCB. And you see here oscillating waves that are resonant modes that would be parasitic for the PCB. So it's something you have to get rid of by adding capacitors. You can really place them with the mouse in 3D, and the model is going to adapt. You see that we have pinned down this oscillating field so that we don't have this resonance anymore. So it's just an example of something you have to deal with when you design such PCBs. Here we are adding, so it's someone working here, we are adding 3D components to the vias of this PCB, and we can look at the same time the model, so the circuit that is built by the software. We call this inside-out electronics. We can follow also traces and look at the signal and make sure that the signal is really going to be readable, like bits, and if the eye diagram is going to be opened sufficiently for bits to be read, so that we don't have failures. If we have problems, we are going to pinpoint the locations where we have problems, and you can see here via, we are back drilling this up to the level of the board, so it's through the board. And you see that while doing this eye diagram is closing, so the eye is no longer sufficiently open, so you can adapt this. You can really make these small changes in the PCB in order to have something robust. We can study the power deposition, the temperature, the thermal stresses, so the structural stresses, if you have oscillations, if there is vibration, is it going to hold or not. The antennas, because the PCB has to communicate with the outside world, so you have a GPS antenna that is coupling with the low voltage data, so differential signals. You can try to see if you scatter this information over broader bandwidths, if this is going to be better or not. So you can have a compromise between electromagnetic integrity and signal integrity. So basically you go through each component of the system. For each component you go through all the physics, all the fields, the temperature. You see the cooling here from the air that flows around the PCB. And from these temperature fields, of course, this will have an impact on the conductivity, on the electronics, and so on. So that's really about making sure that this thing is going to work in a robust way in all possible conditions. In Siberia, in Dubai, different temperatures. Here in Switzerland, in rain. Is it going to work still? And so on. So many questions you can have answered on the computer in this kind of virtual simulations. Here you see the pattern of emission for the antenna communicating with the outside world. So is it going to couple well with the rest of the world, with your emitter, with an antenna positioned somewhere? And now we are going to deal also with the brain, so the software, the embedded software in this chip. This is something we can model as well. So basically here you have a full virtual system that you can interact with. There is a user playing with it. So there are some commands, triggers, change the altitude, change the orientation, the speed. And you see here the reaction of the system, this virtual physical system. And you can just see if your virtual drone is going to be fine, is working fine before even producing it. So the trend now is for companies, for engineering companies, is to plan something, find customers, and then only build it and sell it. So that's an idea, okay, that's a business model. It's a way of interacting with the markets and making sure that you don't risk too much, you don't invest too much too fast. But now what I'm going to deal with today is more how we can use this integrated into physical systems, so cyber physical systems, and how to use this type of models efficiently and make them also usable for machines themselves in order to take decisions, well-informed decisions. Am I going to fly between the buildings or hit the building and so on? So you can simulate all this, that's nice, but you can also train your artificial intelligence with this type of things, because we've seen, okay, the human could control this like a video game. It's a very expensive, complex video game indeed, but you can also use this with artificial intelligence, which is really the interesting topic today. So we've seen a digital prototype, so that's one thing. That's the traditional way of dealing with engineering and science. You plan something, you have assumptions, you model them, you check the model with measurements, and then if everything is fine, you produce. So that's the old-fashioned way. Now, the new way, so actually you are still doing this, but you are using this work, because this is a lot of work. You've created the models, you've created a digital prototype. Now you are going to still keep it and connect it with your digital assets. So it's basically the feedback from sensors in real life, from a system, from a component, different sensors. Here you see a power plant, a gas turbine, so it's something quite big. It's no longer the simple drone, but it works in the same way. You acquire all this as a part of the Industry 4.0, so the idea is to have more feedback from the physical world and bring this together in what we call the digital twin. So this has the advantage of being able to have smarter products doing predictive maintenance in order to have really efficient products that are not going to cost too much to maintain. If you take this example, okay, I think you recognize this in the Gulf of Mexico. This was the old time when human had to take decisions, well informed or not well informed. Now there are some companies who have a vision to make it more efficient, so we go a bit further with the assistance of machines. And the idea here is to have smarter machines than just this one, or the paper and pen, which is still working, is going still to work. Here we are trying to go one step further. So that's what General Electric is doing, for instance. I took this as an example here because they are working together with ANSYS, and they defined this project in 2015. The idea is to have really this kind of digital twin. They created something they called Predix. Okay, that's the trademark name. With the hardware, the software-defined turbine, so this prototype, this digital prototype, bringing together with the data acquisition systems, forming a digital twin, and then a suite of applications for the engineers who have to maintain these power plants. So that's the power plants, that's an example here. Or this blow-off prevention device that was in the Gulf of Mexico on the ground, on the sea ground, and that's created these problems because the engineers on the water had informations they didn't really understand, and they took bad decisions based on these informations. So the idea here is to go beyond just readout of sensors, so you are not plugging a human directly to plain sensor readouts, but you are going to use this data, confront it to a digital twin, see if the twin is predicting the same or not. If it's not the same, then you have a problem because your twin is no longer a twin. But usually, if it's well built, you are going to have a way to extract more information than just what the sensor tells you. Reading the pressure at different locations, you might be able to see with the fluid simulation here what is the actual fluid state in this area. So you have the outputs coming back, and then you are going to take decisions. Another one that is a bit smaller, it's another company who is building compressors. So it's actually a compressor that is sitting at the entrance of ANSYS in Canonsburg in the United States. And it's used as a demo object, a smart object now. So we call this smart because it's plugged to a human-machine interface. You can read all the sensors. You can see here they are displayed on top of the image of the machine. You can connect this to this kind of digital twins. So actually the simulation model that is going to tell you actually the dynamics of the compressor. There is some fluid dynamics analysis, and you're going to be able to take decision, or should I open this bypass valve, another one? How should I tune the valve so that this compressor runs in the best possible way, depending on the loads that is placed on the compressor, because you can never anticipate in advance all the possible load cases for the compressor. It's plugged to something, a black box, that is the system beyond. And here, based on this kind of predictions, you can actually optimize the tuning of the compressor and actually feeds this back, change the settings, and then run in a way that is going to be safer for the compressor or more optimal. So that's an example. Another one, turbine on a turbo reactor. That's another way of having this kind of predictive maintenance. So recuperating data from the field, analyzing it, taking decision, should I maintain, should I do something, or should I leave it running? And this is something that is very interesting, because this is really a disruptive change in the way companies are dealing with their products. So now it's no longer a turbo reactor. This is air transportation or flight time that you are going to sell. GE is doing that, Boeing, they are all, Rolls-Royce is no longer selling motors. They are selling the motor, they are not free, but they are selling maintenance and flight time. A pump is a fluid transportation device, so you transport fluids and you ensure that the thing is going to work. Taxis, ground transportation, and so on and so forth. So this is very interesting, I think, and very positive for the future, because this is a virtuous circle. Since the companies are going to be willing to have more robust products that last longer, so they have success, robust products, and less maintenance and waste. So it's for the better. You are not going to program the thing so that it fails after a few years, just after the warranty. You want to maintain this. So I think it's a very positive paradigm and a new way of seeing actually these components. So if we look at another example.
Just have one question. Do you create just one twin or multiple twins and select the one which is the most optimal?
So the question is, do we create one twin only, or different twins for different parts of a system, for instance? The answer is yes, you can create as many as you want, there is no limit. The definition of digital twin is singular in my slide, but it's not really a problem at all. Since we are dealing with systems, then we are going to have different blocks interacting with each other, and basically each product is a system that deals with the other, so the Internet of Things basically, and this is part of this Industry 4.0. So for each product or each object in the system, you are going to have a digital prototype or digital object that can model it. And if they interact with other components, then we can put them together, basically. So it's really, the answer is yes. There is actually the only limit is us, or the hardware we're using. So here another example, if we focus really on one simple component of a large system. And this is a good example to this question, because here we are going to focus on the braking pads of a car. And we just do the work for this guy here after going to the car. So you can extract real-time data for these braking pads. You can send this to the brain of the whole system. So basically here the system is not even only the car, but the system is all the fleets of all the cars. So if you are Uber, for instance, or if you are someone else like this who has a fleet of many cars, you are going to retrieve the information from all your cars, and you're going to say, okay, should I change the braking pads or not? Based on all these informations that are fed back. And the difference here lies in the way that you cannot tell the car has to be maintained after hundreds of, like maybe 20,000 kilometers. You are going to assess this based on the use of the car. If the car is driving on the highway all the time, you are not going to change the pads at the same time the other. And you don't even want to look at the pads at the garage in order to take the decision. You want the information to be sent back to you, and then trigger an event for the car to change the pads, front or back, depending, So that's the way this gets coupled, so that's the motivation to do in doing that. And now if we look at the model for these braking pads, it's not only the pads, it's the system that controls the pads. So you have the power electronics, the electromagnetic actuator that is closing them, the pneumatic, the vehicle dynamics, the wheel speed sensor that is actually tracking if the wheel is running and at what speed, and the brake pad itself. So if you look at these two blocks, you can see here a magnetic simulation of the closing of this actuator linked to other components. So that's one important piece of equipment. The other one is this wheel that is actually a counter. So there is a magnetic sensor here that sends a magnetic field and reads the change of permeability in front of the, so it's basically a coil with a magnet. So it reads this out, and depending on the change of signal, it will give a velocity for the wheel. So what is important now, because there is some insights that the human has to give to the model or to the machine, we know, and this is by experience, that okay, these tend to break. So we can lose the teeth of this toothed wheel, and if a tooth is missing, then the signal is going to change, obviously. And now when you have an assisted braking event, so you are going to actuate on the brakes, you are trying to brake the wheel without ever stopping it. So when it's working properly, that's the way it will look like. The vehicle speed is going down to 0, it's stopping. The wheel speed is going down continuously as well. The wheel is going to slip slightly, and just when it starts slipping, it moves a bit further, because the valve is going to oscillate here and to counteract basically the sliding of the wheel. So that's this ABS is working properly, and when you have a missing tooth, then you have this problem that actually the wheel speed is going slightly almost to 0, because it misses actually the velocity measurement of the wheel. And this is not so nice, because the valve is going to see harsh events that are going to impact the wear of the brakes. So there is some slip here, the brake pressure, and you see if you miss 2 teeth at different locations, it's even worse. So this is going to have a huge impact on the lifetime of the brake pads. And you can use that basically to trigger a change event, not only on the brake pads, but also on this wheel. Because if you change your brakes but you don't change this, then you are going to have your car run even longer and always wear the brakes out. So it's a kind of smart way with a very simple case, very simple model. So it's one digital twin, but then in the car we have many others. So you see here basically what the sensor will see, or the AI that deals with this information. The nominal sensor, we have here the spectrum of the magnitude of the sensor. So it's a Fourier transform of these signals we've seen before here over time, here over frequency. So the working one, the missing, 1 tooth missing, two teeth missing, so you can see the difference. You have to train your machine or your brain basically that is going to analyze this with this type of plots. And then when you have the information, you can infer the wear of the pad. You have a 3D model that tells you, depending on the pressure and the dynamics, how much wear over time. So it's something that is going to be increased. So cumulative wear or instantaneous wear is going to be accumulated throughout the lifespan of these braking pads. Here you have another example, sensor malfunction. So the wheel is just braking and stopping. And you see that there is no cumulative wear. Okay, that's a simple example basically of a wheel that is not going to, so is no longer working properly with the ABS anti-blockage system. I have another example here I can show you with, so basically another smart system. It's an interesting one because I took something that is really not so smart, and just to show you that we can make pretty much anything smart. The smart soccer ball. So what is the smart soccer ball? If you feed it, you fill it basically with the same electronics as before, but with another functionality, then you can have the so-called smart ball. So it's something that allows you to measure the position of the ball, the speed, the path it takes, the accelerations, if there is a goal or not. Just because of this electronics, is going to communicate with some device, a watch, a phone, a computer, on the field. So this is something now that is used on the soccer fields, and that you can also almost buy from the market. There are some startups doing that as well. So you see the acceleration sensor, so that's the modeling of the acceleration sensor that gives you a signal back on the electronic readout. Again, this PCB is everything working fine. You can look at the pattern for the emission of the antenna. Is it going to communicate with my smart device, with my smartphone? Is that going to be fine or not? And then some additional physics around the ball. How is it flowing into air while it's spinning and so on? So you can really predict even the trajectory or check the trajectory before the ball has reached the goal, for instance. Or you can, okay, here it's about just charging the components, the battery, with an inductive coil. So it's inductive charging, so that's basic stuff basically. And once you have this, you can see, okay, you can plot the trajectory on your smartphone, see it in 3D, try to teach yourself. Basically, it's no longer about machine learning, but about the human being that is learning how to kick this ball in the best possible way. And we can even think about an electronic that is teaching, a coach that is teaching how to shoot in the corner of the goal. You can see here the detection when the ball enters the gate, and you see here the electric field basically that is impacted by the passage here of the ball, and the device that is going to be reading out that the ball is really in the goal. So there is no possible discussion. And sending this information to an antenna, to a relay, and to the rest of the electronic. So you see there is the ball itself is a system, and then it goes beyond. Everything is interconnected, and that's the interesting stuff and the very exhilarating new developments with all this type of objects, of smart objects interacting in the Internet of Objects, Internet of Things. So you see here, he receives the information, oh yes, there was a goal. Okay, at least the human-machine interface here was not complex to create, it just says goal. So you see here, for this very simple example, all the possible places where we are using simulation, or our customers are using simulation. And now, of course, you can think about other applications. There is no limits, basically, and this is the typical kind of thoughts and reflections that are going to define what we are going to do as engineers in the future. This is my point of view, basically. We are not going to be doing the same job in the future than now. Thinking wider, putting these things together, and answering this type of questions, or letting the machines answer this type of questions for us. So the digital twin, or the machine that is willing to learn, has to be able to answer this type of questions. What happened in the past? What could happen in the future, given a sensor readout? What should we do to improve the device, to change something, or to optimize the running of the pump, of the compressor, of the ball? Having an advice for the user of the smart soccer ball. Okay, please try to shoot slightly, so 1 millimeter to the right in order to gain a few meters at the goal. I don't know, these kind of things, and visualizing the curve of the ball, or just adapting to what the guy is doing. The ball is not active yet, it's a passive device. That's good, because otherwise we would have a few problems at the end of the match if the goal could be able to impact the trajectory. So here is about analytics, big data analytics. So these questions here, it's called descriptive analytics, what happened in the past, predictive analytics, what could happen in the future, and so predictive and prescriptive analytics, how could we improve something, how could we change something in order to make it better. And this is the type of things that we are going to feed back to the users, to the human beings who are trying to use the smart device. So it's simple to ask, but it's not simple to answer. So, of course, since all these models are digital, they are made of bits, who else than machines are better placed to analyze this data and to make use of it? Of course, for the users, for the engineers, we are simulating something and then we create nice plots with colors and so on, whereas the machine can get already the information directly, and it's easy to couple with a result of a model, of a simulation model. So the idea now is to see, if I take another example here, that would be the automotive industry. What the machine could see that we never see, basically, when you are on holiday, you are driving to France, typically, through the péage, and you see the car is arriving, and this door is going to sense the incoming car and charge you some money for the trip. So that's the simple thing that is already working, but now we are trying to make this even smarter. So we want the car to be able to drive itself on its own. So we are adding all these sensors to feed the machine with the relevant data. So you have the central computer and all these sensors, different wavelengths, these different ways of interacting with the world. So the adaptive cruise control is something you can have now in any new car, just keeping the distance with the front car, and all these other sensors sensing in the area, so the area around the car, high frequency or acoustic for the park sensor. So it's something very actually that is in almost every car at the moment. But now the question is, how can we go beyond just parking automatically, just also driving automatically? So here we see in the software how this kind of crossing event is dealt with. We launch rays, basically, because we cannot calculate these electromagnetic waves with small wavelengths over such a big model. So basically we are going to interact with the so-called shooting and bouncing rays. So it's a technology that is used, so it's no longer exactly the finite elements modeling I was speaking about in the beginning, but it's just about sensing the position of a car, reflections from it for radars, for instance. So if you see what the machine looks or would get as an information, so here you see the range, the distance from the radar, the velocity from the radar. So here positive is the car coming in front. So you see this car here that is driving at a relative speed of about 30 kilometers an hour. So sorry, meters an hour. It's a bit faster. And here what you see is actually the reflections from the ground, because the ground is also moving towards the car. So you have these reflections that are actually annoying because they might hide you details. So you see you have to fine-tune your radar, the frequency they are working at and so on, in order to have a clear view. Since the machine is not looking at exactly the same thing as what we do, we have to adapt with this other physics. So in a way the machine is able to see things we don't see. In another way, something that is obvious to us is going to be hard to identify for the machine. Another one, so it's about scenarios now. So we are going to create virtual scenarios of interaction with the environment, trying to look at, okay, what could be the effect of this guardrail, for instance? Okay, because in the other model it was not inside, we forgot it. And now we see that the guardrail is something that we see on the vision of the machine. So basically this car sees everything here. So you see here with minus velocities, that's the truck, these large trays, the car in front of the truck. So actually that means the computer can see this car whereas the human cannot, which is interesting. It's already something, if the truck is too big, then you cannot see through, but the radar can. So it's already more information than the human being is able to see. The guardrail, as I said, is coming towards the car relative to point of view of the car, and it's viewing actually the radial distance. So you see that the guardrail is actually fainting here to 0 velocity radial distance once it's shooting past the car, basically. So that's this effect there. And you see the other car coming in front with a positive relative velocity. So what you want to avoid is not this, but of course this as well, but especially this one, because this is the most dangerous thing in this configuration. So that's what is done with this type of analysis. Different scenarios. Now you see the car in front, and there is a big truck carrying money, so it's made of steel, and it's going to hide the other car because the waves have to go around. So you see here the car is trying to communicate with this car. It's not only passively interacting with the world and looking at the world, but now it's going to speak with the other one because we have an Internet of Things, and the cars are going to speak together. And you see that this has an impact on what the car receives. It has to understand, okay, there has some other truck coming in between. I have to brake a bit to keep the distance, safety distance, and so on. So that's what the automakers are studying with this type of tools, the antenna, how it interacts with the world, and scenarios. Another scenario, you can take the whole city as well. Drive through the city, there is an emitter that you are going to use in order to know your position. Since the city is full of waves, then you can use these waves for your positioning, in addition to the GPS. So you can fine-tune the position using any emitter in the city, and by learning what you have where while you are driving, you can actually refine your position. We can see here actually the position, so the spectrum basically, and the amplitudes for different positions in the city from this antenna that is emitting. So it's really a way to go beyond what the human being can sense with this type of measurements. So basically now if we look at large companies like Continental, they have plans, of course, they always have plans, roads, maps, which is good for this type of application. The name is well chosen. So you see here what we are doing now. They call these technical enablers for autonomous driving. So it's basically having the sensors, having all the feedback from the reality that is needed for the AI or whatever is going to drive the car here. So basically the goal is there is obviously no axis here, so no information of year, and that's on purpose because I guess no one can really define when this is going to happen. We don't have a model yet for that. So basically automation is going to increase. This is at least what they want to have happening. Fully automating parking scenarios. So we are already there actually. Stop and go, cruising, highly automated, so we can take the hands off the wheel, but for legal reason, obviously you have to stay behind. Highly automated construction sites. Okay, that's for the production. It's more important, and then the driving, the autonomous driving. So that's the way they see it. And now about the question of how much time do we need to have autonomous vehicles on the streets. We have different sources that are saying, okay, we need hundreds of billions of miles still to have enough data to feed or to teach an AI or to have something that is safe. Okay, that's a statement from one source. Akio Toyoda from Toyota is a bit more optimistic. He says 8.8 billion miles. But that is interesting. He says including simulation. It's not only measuring on the field, it's just now having these scenarios in silico and having large clusters running with all these scenarios in order to train the autonomous vehicle. At Bosch, they are looking at the money, so the expenditure for validation in hours, 10 to the power 6 to 10 to the power 7. So it's really quite a lot. And we compare this now to what Google has been doing. They have these autonomous vehicles that they have been driving with someone behind the wheel always, but they have totalized 2 million of miles, which is really nothing compared to this one. So at this pace, they started in 2009. So we still need about 40,000 years in order to fulfill this statement here at this pace. Of course, we are going to look at accelerations, simulation, more cars on the streets and so on. But it's already giving a kind of information that, okay, we are not going to go there if we don't simulate, if we don't use digital twins in silico in order to train the AI to test all the possible failure scenarios. So we look at now this way. We have the technology, all the sensors, the radars installed, the interaction with the environment, all these scenarios. You see here the radar, the interaction with pedestrians, with all sorts of things that are going to show up, because usually reality doesn't look like this, so you don't have only 3 trees on the street. So there is still some work to do. And then we are looking also at the intelligence behind the embedded software. Of course, ANSYS has solutions for this as well, so you can program everything into this V development loop. So you are going to plan for the system, for the safety, for the architecture, for each component, and then you are going to validate them. This is typical V structure in production of embedded software. And this is able to communicate with the modeling. So basically, within one company, they've built all the possible tools, not all the possible, but all the tools that are needed, and they are going to expand this because they've identified this type of development as really critical for the future. And yeah, so you are going to collaborate dynamically between these and the simulation tools. So with this, you can have in silico the full loop for this advanced driving assistance. So the full loop looks like this. So now if we zoom at these type of things, okay, you have drive scenario models. So there is lots of work behind. So we start with this drive scenario models, sensor models. What does the machine really see? So we get this from the models. Signal processing, sensor. With the sensor, taking into account what the sensor can do and see and cannot, all the limitations in all possible configurations. The algorithm, human-machine interface, if at all still needed, at least for the testing. The vehicle component, so compartments. So okay, yeah, that's vehicle component, excuse me. And the vehicle dynamics models. How is the car interacting with the field, with the roads? Is it going to slide, to tilt, and so on? So you can really have this type of models. You already have some small of low-level models. When you are driving a curve, the car compensates and drives you through the curve so that you don't go in a twisting figure, which is already very nice. So it's based on models. Here, okay, we try to bring this a bit further, basically, with even more physics into the model and into the intelligence. So if we look at the past, we have the analytics. So from the big data, we can get analytics. So that would be the first basic step. And then the idea is to leap, to add physical meaning to this data analytics from these models, in order not to have to train the AI in everything, because okay, you can teach a kid, or you can let him teach himself. He might have some problems, he might fall, injure himself, so it's the dangerous path, letting the kids try to evolve on itself. Or teaching the kids with some models of reality, okay, if you touch this, you are going to burn yourself. Then they are still going to try it. But at least they understand quicker if you told them with a model first. So the idea here is to add these physics insights into this digital world in order to have a complete system simulation, to have predictive analytics, prescriptive analytics, and operational optimization. So here this is for experts, for alerts, anomaly detection, so this is what we already have. And then it's going to speak also to the management of the company. I mentioned the fleet of cars. It's not even a car, it's a fleet of many cars. And there is a manager somewhere telling, okay, I see that we are investing too much now in brake sensors. We are going to increase the risk, fine-tune the analytics in order to change them really at the last minute. It's a bit dangerous. But if you have the proper tool, you might be able to do that. Or you can increase safety of users for all these cases where the tooth wheel broke and that led to improper braking that led maybe to an accident. So you can really prevent this by the predictive analytics. Some things that would have been the one in 1 million that, or in several hundred thousands that went wrong. And okay, maybe it crashed, no one ever knew why, but it happened. So the idea is to be safer from this point of view. So if we look at our evolution, okay, don't ask me why this guy is going to be naked again. So yeah, never ask for. There is a next step. Maybe the machine is going to overtake us and take us by the hands. I already have this kind of feeling when I take my smartphone. But sometimes, okay, it's not me guiding the smartphone, but him guiding me. Especially when I take the car with the GPS. Okay, that's already almost that. It's telling me, okay, expected arrival time, taking into account the traffic. So the traffic made by all these other users, the Internet of Things, of objects that are traveling at different speeds, and basically these very simple speeds and location measurement is going to predict your arrival time. So think about this for all type of objects we are using. And yeah, for the last step, when the machine overtakes us, of course it's a bit scary, because you can see now that machines can optimize themselves. If you take this robot, so it's a robotic arm from a manufacturing company, feeding the info to our software, we can let the software find a new shape. It looks like a bone structure, so you see that the software is already able to evolve in a few minutes what took the human bone a few 100,000 of years to achieve, and creating different shapes. And now it can print itself as well, so it can print composite materials, so elastomers, or even steel, titanium, and so on. So yeah, we are not far from the machines improving themselves, printing themselves. Yeah, okay, we're not there yet, but it's just a very simple example from the industry, and another example from the car that we are going to take afterwards to go back home. You can improve this topology, and you can print this with a structure inside. So you might not even see it, but it's there, and it's lightweight structure. It's very interesting stuff that is that we are dealing with here every day in my company, which makes the work very, very interesting. And I would be really happy to see these kind of models more closely used by you guys who are dealing with machine learning. So I've showed a few examples, mostly from the United States. They are very active in this, in China as well. And in our country, in Switzerland, in Europe, okay, there are things going on. GE is also in Europe now, anyway. But yeah, there can always be more, actually, in the labs or in the industry. Okay, so I'm through. If you have any questions, I would be really happy to answer before the beer and while we have the beer.
So maybe I have a question.
Yeah.
So when you create a simulation, can you use it to, let's say, legalize some of the enablers? Let's say, in normal case, you would have to crash some cars, you have to make a lot of empirical tests.
Yeah.
Can you use your simulations, are they enough accurate or accepted, I would say, like this?
Yeah, so is the simulation, is the model usable to validate something for regulation from the point of view of safety? You mentioned crash tests for the cars. So the answer is yes. And usually when the life of someone is involved and the test is possible, there would be validation of all the prototypes, everything. And then there will be only one pre-series, not even a prototype, but a pre-series that is going to be slammed into the wall. If we take the car, for instance, the crash tests now are done virtually in the software. You can see the car crashing against the wall. You do these hundreds of crash tests virtually, and then you build a few cars from the series, basically. You crash them to just validate what you did in order to see if the human has not done a mistake. Because of course the software just does what you tell him to do. And there is always a responsibility behind, so the wise human is usually checking what he did. So usually, yes, you can in a way assess something with the simulation. But usually companies still like to validate this with the last step. Just once, at least to be sure. There are some cases where you cannot really measure. So if you send a rocket to the moon, you are not going to test everything, or you cannot test the full launch and everything. So you test what you can, and you simulate the rest. So it's complementary. The question of measurement, simulation, it's always complementary. It's a tool like any other that you can use wisely or not. You can make mistakes with the tool. But there are some cases, for instance, for implants in human beings, where the FDA is going to accept simple measurements, simple load cases that are not really what will happen in an implant. If I have an implant here on the leg, the tests are going to be apply a force in a few directions, and then you simulate and you assess for other load cases with the simulation. So you can do that. So this type of way of implanting something that is not possible to measure without killing someone, this is the case where you are going to rely on the simulation. For instance, a stent, an aortic valve mounted on a stent. So if you implant this to a human being, so either he survives or he dies. So you are going to do this in the virtual world on the simulation. Then you are going to test on a pig. You kill a few pigs, and then the site is quite similar. You have simulated, so you have good reasons to think that is going to be applicable on the human as well. And then you try it. And the validation is done through the several operations. So that's this kind of answers I can give now, or examples that come to my mind at the moment.
First of all, thank you for your presentation. I think especially for this this way of failure-proofing the systems, it looks very, very interesting what you're doing. And the only point I want to make is about this self-driving car, this ADAS project.
Yeah.
The way I understood it, I'm not in the field, but I think that most of the modern approach to self-driving cars are not actually using a completely model-based approach like yours. Mm-hmm. They are using a reinforcement learning approach.
Yeah.
So they are trying to infer policies from outcomes rather than from a model. And the idea behind this was to not have to have these complete models, these complete simulations that we used to have for many physical problems. What's the main selling point of your approach compared to these reinforcement learning approaches for self-driving cars?
Okay, so for the ADAS, what is the main selling point of using a completely virtual model, the full loop in the virtual model, compared to a reinforced information based on field measurements, if I understood well, plus the addition of the model. Is that right?
Yeah.
Yeah.
It means that when we're talking about the child that learns from experience,
yeah,
and you're actually teaching them some valuable lessons. The approach now in self-driving cars is mostly learning from experience, like from sensors naturally from your experience, sensory experience. But still, reinforcement learning models are based on the idea that you can learn strictly from outcomes, and I think that's what Google self-driving cars are doing. And not from complete simulation with the trees and the telescopes.
So strictly from outcomes from the fields instead of simulation. So basically, of course, the presentation is of course orientated towards fully numeric and virtual assessments. It's of course a selling presentation. And the reality is of course a hybrid between both. It's complementary, as I mentioned, real life measurements and model-based measurements basically, or simulations, are complementary. I think the answer to that is very simple in terms of mileage that is required to have all the data in order to have something that is fail-safe. And you want to send your kids in, and that is going to drive next to your kids. It's just so huge that you have to help a bit with these simulation-based insights. So it's not exclusive at all, actually. It's
regulators would be more inclined to accept self-driving cars if they are based on more simulations than strictly outcome-based or reinforcement learning-based.
I would put it this way. I think if you measure everything you can. So it takes you 10 years, many hundred cars. And then anything you add for the regulations is always a good, is a given, is an asset when you have to defend your case, basically. So you're going to fight to have a regulatory body that accepts what you are doing. So basically, failing to use state-of-the-art tools is already a failure, because that means you could have done better. So that's maybe, if we put it this way, trying to use all possible tools available and not only one. So of course, not only simulation. It's the same arguments for not only simulation, but also measurements on the field. And of course, because you are not going to think about every kind of events, like the plastic bag on the highway. Am I going to brake or should I go through? It's something hard for the AI to define or to decide, and in addition to the model. So who has thought about the virtual plastic bag? So for this type of things, of course, the field is crucial. And I would, as an engineer, I would not sign off something that is completely virtual, even if I'm doing this every day. I mean, we are interacting with companies and we are complementary. We are relying also on this field experience. That is fundamental, yeah.
On the other hand, if you want to train a reinforcement learning-based algorithm, you will need actually a lot of simulations, right? Because you cannot train a reinforcement learning-based agent on the street.
Indeed, but it depends on the kind of indeed. It depends probably on the kind of sensors that you have. But yeah, for the first steps, naturally you need at least some kind of a simulation, but not an a posteriori simulation, but this one like a much more simpler simulation.
Mm-hmm.
And then probably like the data that you would want to create for your simulation-based model. Your reinforcement learning-based model. I'm not reinforcement learning, but probably you would have a sensor on a car that is not driving itself. Like you would drive the car yourself and take pictures, and then use these pictures to train your reinforcement learning model.
This is more supervised learning approach, right?
Yeah, I see what you mean. Yeah, you would have a simulation. Yeah, sometimes naturally.
So you can help the simulation world with the measurements, and in the other way as well. So maybe we can go on with a beer around this topic, because I think this is the kind of topics that can go for quite a long time. It's very philosophical as well.
So maybe last question, and if someone would like to ask
you
something
too.
else. So no. So thank you very much for everything and for your presentation. And
thank you.
I have only a little announcement. In the middle, or we don't have still that date. In middle of February or end of February, we're gonna have another meetup. We don't have it in January because there are machine learning days at EPFL. So I invite everyone for enjoying. Those are 4 days of workshops and conferences given by really good speakers. But next meetup gonna to be on machine learning.